There is a question that sounds perfectly reasonable and turns out to be empty. What came before the Big Bang? Ask it carefully, and the words dissolve, the way asking what lies north of the North Pole dissolves. Tonight on Midnight Science, we walk slowly back toward the beginning until the idea of before stops making sense. If these quiet journeys help you rest, a like and a subscribe keep them coming. Tell me where you are listening from tonight and what hour it is where you are. Settle in. We have a long way to go. There is a stone in your hand, small enough that your fingers close over it completely. Smooth, the way a river makes things smooth, over a span of time that has nothing to do with you. Feel the weight of it settle into your palm. Feel the cool of it warm slowly against your skin. Now run your thumb across the surface, slowly, in a long, unhurried arc, and keep going, around the curve, over the top, down the far side, and back again. Notice something as you do this. There is nowhere on that surface that counts as the beginning. You can travel across it forever. Your thumb can circle it 1,000 times tonight and it will never arrive at an edge, never come to a rim, never find the place where the stone starts. The surface is finite. You could measure it. You could wrap a thread around it and read off the length, and yet nowhere on that finite surface is there a first point, a boundary, a lip where the stone becomes not the stone. The surface simply closes on itself, quietly, without announcement. Hold the stone. We are going to come back to it. For now, set it down beside you, or keep it in your hand if that is more comfortable, and let us talk about something that almost everyone pictures wrongly, including many people who study it professionally, and including, for a long stretch of the 20th century, some of the people who invented the idea in the first place. Let us talk about what the Big Bang was not. Here is the picture most people carry, and it is not a shameful picture, and it is not any one particular fault. It arrives through language. It arrives through the words themselves. Big Bang. 2 syllables that between them summon a very specific image, and the image is this. There is a darkness, an enormous void, empty and cold and already there, stretching in every direction. Somewhere in that void is a point, tiny, dense, packed with everything that will ever exist. And then, at some moment, that point detonates. Matter flies outward through the surrounding dark. A shockwave expands. Debris scatters, and over billions of years the debris cools and clumps and becomes galaxies, becomes stars, becomes the carbon in your hands, becomes the stone. It is a vivid picture. It is also almost entirely wrong. Let me say that again so it registers. The picture almost everyone carries of the beginning of the universe is not a simplification of the science. It is a different thing altogether, describing a different kind of event in a different kind of place. Take the picture apart with me, piece by piece, and notice how much of it dissolves. Start with the void. In the popular image, the darkness exists first. Space is already there, empty and waiting, and the explosion happens inside it. But that is precisely what the theory does not say. There was no waiting room. There was no surrounding emptiness for the young universe to expand into. Space was not the stage. Space was part of the performance. The expansion was not motion through space. The expansion was the stretching of space itself, and there was no outside for it to stretch into. Now, take the point. In the popular image, there is a location, a specific address, a place you could in principle travel to, the site of the explosion, the cosmic ground zero. Astronomers would be able to look at the sky and say, there, that direction, that is where it happened. But no such direction exists. There is no address. Every measurement we have ever made says the same thing, which is that the expansion happened everywhere at once. Not at a point, everywhere. And here is the part that is genuinely difficult to hold, so take it slowly. The expansion happened here, in the volume of space where you are lying right now, in the room, in the bed, in the space occupied by your own body. 13.8 billion years ago, the material that would eventually become the walls around you and the air in your lungs and the iron in your blood was part of a hot, dense state, and that state was not somewhere else. It was here. It was also everywhere else, simultaneously. Every region of space you can point to, every distant galaxy, every gap between galaxies, every cubic centimeter of the observable cosmos was involved. The beginning did not happen at a place. The beginning happened at every place. Let that land for a second. You are not looking outward at the site of the explosion. You are inside it. You have always been inside it. There is no vantage point from which you could have watched. And take, finally, the shockwave. In the popular image, matter flies outward through a stationary void. And if you were standing far enough away, you would see it coming. But galaxies are not flying through space like fragments from a grenade. They are, for the most part, sitting more or less still in their own local patch of space. What is changing is the space between them. The distances are growing, not because things are traveling through the gaps, but because the gaps themselves are getting longer. That is a strange sentence, and it deserves a moment of your attention. The distance between two objects can increase without either object moving. That is not a trick of language. That is what general relativity permits, and what observation confirms. Space is not a passive container. It has geometry. That geometry can change, and it has been changing steadily for the entire history of everything. So how do we picture this without importing the wrong image again? The oldest teaching tool is the balloon, and it is worth walking through carefully, including the places where it fails, because naming the failures is part of being honest with you. Imagine the rubber surface of a balloon, partly inflated. Draw small dots on it with a marker, scattered evenly, and let each dot stand for a galaxy. Now blow more air into the balloon. Watch what happens to the dots. Every dot moves away from every other dot. Not because the dots are sliding across the rubber. The dots are painted on. They stay exactly where they were painted. What changes is the rubber between them, which stretches, and so the distances grow. Sit on any dot you like, choose any one at all, and from that dot the view is identical. Every other dot recedes. Nearby dots recede slowly. Distant dots recede faster because there is more stretching rubber between you and them. And here is the important part. No dot is the center of the expansion. Search the surface for the origin point, and you will not find one. Every dot has an equal claim. Every dot sees itself as the still point around which everything else is drawing away. That is the essential geometry, and it is correct. Now here is where the balloon lies to you. The balloon has an inside. It has air in it. It has a rubber skin with a thickness, and a room around it, and a person blowing into it. All of that is extra. None of it corresponds to anything. The analogy only works if you agree to live entirely on the two-dimensional surface of the rubber and to forget that anything else exists. The moment you allow yourself to picture the balloon sitting in a room, you have smuggled back in exactly the thing we are trying to remove, which is a surrounding space for the universe to expand into. The balloon also has a center at the middle of the volume of air, but that center is not on the surface. It is not part of the model. It is an artifact of drawing the picture in 3 dimensions, when the model only has 2. So the balloon is useful and the balloon is misleading. Both are true. Keep both. The other old teaching tool is bread, and it fails in a different way, which is instructive. Picture a lump of dough with raisins scattered through it, sitting in a warm kitchen, rising slowly. As the dough expands, every raisin moves away from every other raisin. A raisin 2 centimeters from you drifts a little further off. A raisin 10 centimeters away drifts off 5 times faster, because there is 5 times as much expanding dough in between. Again, no raisin is doing anything. No raisin is swimming through the dough. The dough is doing the work. This version has an advantage over the balloon. It is 3-dimensional, which feels closer to the world you live in, and the sense of things being carried along passively by a growing medium is exactly right. But the loaf has a surface. It has an outside edge where dough becomes kitchen air. It has a center, a raising closest to the middle, a raising closest to the crust. The universe, as far as anything we can measure tells us, has neither. There is no crust, there is no oven, there is nothing the dough is rising into. Every analogy we have leaks in the same place. Every one of them, without exception, gives you an outside, and the outside is the one thing that must not be there. This is not a failure of imagination on the part of the people who build the analogies. It is a limit built into the equipment you are using. Your intuition was assembled over millions of years by ancestors who needed to judge the distance to a predator and the depth of a river. It was assembled for objects inside a space. It was never asked to picture a space that is not inside anything. The fact that the picture will not form cleanly in your head is not evidence that the physics is wrong. It is evidence that you are a primate holding a stone. Hold that for a moment. Now, where did any of this come from? Not the popular image, but the actual idea, because it did not arrive as a revelation. It arrived the way most real things arrive, through patient work by people who mostly did not live to see it settled. In 1927, a Belgian priest and physicist named Georges Lemaitre published a paper in a journal that very few people outside Belgium read. He had been working through the equations of general relativity, the same equations Albert Einstein had published a decade earlier, and he had noticed something that Einstein had noticed too and had actively disliked. The equations did not want to describe a static universe. Left alone, they described a universe that either expanded or contracted. Einstein had added a term to hold his cosmos still, because a still cosmos was what everyone assumed the cosmos to be. Lemaitre did not add the term. He followed the mathematics where it went, and where it went was outward. He also went further, which is the part that took real nerve. If the universe is expanding now, he reasoned, then run the film backward and everything was closer together in the past. Keep running it backward and you arrive at a state of enormous density. He called it the primeval atom, a single quantum from which everything unpacked. It was speculative, it was thin on evidence, and it was published in a place where it sat mostly unread for years. He was not celebrated for it. He was, for a while, gently ignored. Meanwhile, in California, a former lawyer and amateur boxer named Edwin Hubble was doing the unglamorous half of the work, which is measurement. Night after night at the Mount Wilson Observatory, working with a telescope that required him to sit in the cold and guide it by hand, he was photographing faint smudges of light. The question at the time was whether those smudges were clouds of gas inside our own galaxy, or whether they were entire other galaxies, unimaginably far away. Hubble, using a method of distance measurement developed by Henrietta Swan Leavitt, showed that they were the latter. The universe was suddenly much larger than anyone had thought. Then he did the second thing. He measured how the light from those galaxies was shifted toward the red end of the spectrum, and he compared the shift with the distance, and a pattern appeared. The further away a galaxy was, the faster it appeared to be receding. Not one or two of them, all of them, in every direction, following a relationship you could draw as a line on a graph. That relationship is exactly what the dots on the balloon would show you. That relationship is exactly what the raisins in the dough would show you. It is the signature of a stretching space, and there it was, written in starlight, measured by a man sitting in the dark with cold hands. I want to be careful about how this gets told, because it usually gets told as a story about genius, and it is not one. It is a story about patience. It took Lemaitre years of working through equations that most of his colleagues thought led nowhere. It took Hubble years of individual photographic plates, each one a full night, each one a small measurement subject to error, accumulating slowly into something that could not be dismissed. It took Leavitt, working as a human computer at Harvard, cataloguing thousands of variable stars by hand, to make the distances measurable at all. Nobody sat up in bed with the answer. The answer was assembled, plate by plate, over decades, by people doing careful work in the reasonable expectation that they might be wrong. That is what discovery actually looks like. Slow, distributed, mostly unwitnessed. Still, an expanding universe was an idea, and ideas can be argued with. Many people did argue. Through the 1940s and 50s, there was a serious, respectable, well-argued alternative, in which the universe had always looked roughly as it does now, with new matter appearing gradually to fill the gaps as things spread apart. No beginning, no dense state, just a cosmos that had always been running. Some very good physicists preferred it, partly on aesthetic grounds, partly because a universe with a beginning felt uncomfortably like a universe that required an explanation for its beginning. What settled the argument was not an argument, It was noise. In 1964, two radio astronomers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna that had originally been built for satellite communication. They wanted to use it for radio astronomy, and to do that they needed to understand every source of noise in the instrument. So they set about eliminating them, one by one. There was a hiss, a faint, persistent static that would not go away. It did not change with the time of day. It did not change with the season. It did not change with the direction they pointed the antenna, which was itself extraordinary, because almost every real signal in the sky is stronger in one direction than another. This was the same everywhere they looked. They checked the electronics, they checked the wiring. They discovered that pigeons had been roosting inside the horn and had left a white dielectric residue on the interior surface, so they evicted the pigeons, cleaned the antenna thoroughly, and measured again. The hiss was still there. What they were hearing, it turned out, was the oldest light in existence. Roughly 380,000 years after the beginning, the universe had cooled just enough for the fog of charged particles, filling it to settle into neutral atoms. Before that moment, light could not travel freely. It scattered constantly, the way headlights scatter in dense fog, and the cosmos was opaque. At that moment, the fog cleared, and the light that happened to be traveling at that instant was released to fly onward. It has been flying ever since. It has been stretched along the way by the same expansion that carries the galaxies apart, stretched from a fierce glow into faint microwaves, cooled to a whisper just under 3 degrees above the coldest possible temperature. And it is arriving now. It has been arriving the whole time. It is passing through the room you are in as you listen to this. It is passing through you. Sit with that. Two men cleaning bird residue out of an antenna in New Jersey found the residue of the beginning. They did not know what they had. It took a conversation with a group of physicists at Princeton who had been theorizing about exactly such a glow and preparing to look for it before anyone understood what the hiss was. The theorists had predicted it. The engineers had found it by accident while trying to get rid of it. That is often how it goes. After that, the argument about whether there had been a hot, dense beginning was effectively over. Not because someone won a debate, because a measurement existed, and it was the same measurement in every direction, and no other picture could explain it. Since then, the measurement has been repeated with far greater precision from space, mapping the tiny variations in that ancient light across the whole sky, and every refinement has told the same story. The universe was hot. The universe was dense. The universe has been expanding for 13.8 billion years, and the expansion happened everywhere. Which brings us back, finally, to the thing that will not sit still. If the expansion happened everywhere, and there was no point of origin, and no surrounding void for it to expand into, then what, exactly, was around it? Ask the question honestly, and watch it start to slip. Around implies an outside. Outside implies a somewhere. Somewhere implies space. And space is the thing that was expanding, so it cannot also be the thing doing the surrounding. The question eats its own foot, and yet it does not feel like a broken question. It feels like a perfectly reasonable thing to want to know. The words are all ordinary words. The grammar is unimpeachable. You can say it out loud and nobody would stop you. I am not going to answer it tonight. Not yet. I want you to notice the shape of it and then leave it where it is. Because there is another question with exactly the same shape waiting for us further in, and it is the one this whole walk is really about. For now, just register the sensation of a sentence that is grammatically fine and physically empty, of asking something the universe may simply not contain an answer to, not because the answer is hidden, but because the question was never quite a question. You will feel that sensation again. The stone is still in your hand. Run your thumb across it. No edge, no beginning, just surface. The stone is still there. Leave it in your palm. Now imagine that everything you have ever seen was recorded. All of it. Every galaxy and every star and every particle on a single length of film. 13.8 billion years of footage. And imagine that you have been handed the reel and told you may run it in either direction. We have been watching it forward your whole life. Tonight we are going to run it backward. Not quickly. That is the important part. There is a way of doing this that takes 90 seconds and ends in a flash of light, and it teaches you nothing because it moves too fast for anything to become real. We are going to do it slowly, stopping at each stage long enough for you to stand there and look around before we go deeper. Some of these places you could survive for a moment. Most of them you could not. All of them were once the entire universe, and every atom in your body has been through every single one of them. Start with tonight. The galaxies are drifting apart, not violently, slowly, patiently, with the gentleness of something that has all the time there is. Now reverse the direction, and they begin to close. Nothing lurches. The nearest large galaxy to ours creeps a little nearer. The distant ones, the ones whose light has been traveling for billions of years, begin to draw in from the edges of the visible sky. Run it back 1 billion years, and the change is barely worth mentioning. The sky would look familiar. The same kinds of galaxies, the same spiral arms, the same slow rotation. Our own galaxy is a little younger, a little more full of gas. The sun is a middle-aged star with a warm planet under it, and on that planet nothing has yet crawled onto land. The universe at this point looks like a slightly earlier draft of the one you know. Keep running. 5 billion years back and the sun is not there. It has not formed yet. Where the solar system will be there is a cold, thin cloud of gas and dust, part of a much larger cloud, drifting between stars. The carbon that will be in your body is in that cloud, and it is not yours, and it has already been through the inside of a star that died before the sun existed. Everything heavier than helium in your hands was manufactured in a stellar interior and released when that star came apart. You are made of the discarded material of a previous generation. 10 billion years back, and the galaxies have crowded closer still. They are smaller, bluer, more chaotic. They collide often. They are making stars at a furious rate compared with today, burning through their gas, lighting up. The sky, if there were anyone with eyes to see it, would be brighter and more violent than anything you have ever looked up at. 13 billion years back, and the first stars are being unmade. Understand what that means in reverse. Their light is being drawn back into them. Their heavy elements are decomposing into the hydrogen and helium they were fused from. And then those stars are gone, dissolved back into cold gas, and the universe is dark. Not dark like night, Night has stars in it. This is dark with nothing in it at all. There is a stretch of cosmic history that goes by a name that sounds almost medieval, the Dark Ages, and it earns the name honestly. Hundreds of millions of years in which the universe consisted of neutral hydrogen and helium, thin and cooling, with no source of light anywhere in it, no stars, no galaxies, no fires, just gas, slowly gathering itself under gravity, doing the invisible preparatory work that would eventually ignite. The universe spent longer in that darkness than the Earth has existed. Let that land for a second. Now keep going backward, and something changes. It gets warmer, not warm as a room is warm. This is the whole of space having a temperature everywhere, with no cold place to move to. Run it back far enough, and the temperature of the entire universe rises to something like the surface of a hot stove, then hotter. Somewhere in here, going backward, you pass the moment when the ambient temperature of all of space was roughly the temperature of a comfortable afternoon, and then the temperature of a hot bath, and then the temperature of an oven. And there was no shade, and no shadow, and nowhere at all that was cooler. Keep going. The gas begins to glow, and now we arrive at a wall, and it is the most important wall in observational astronomy, and you have already met it once tonight. 380,000 years after the beginning, running forward, the universe cooled enough that free electrons could attach themselves to protons and settle into neutral atoms. Run that backward and you watch it come apart. The electrons are stripped away from their nuclei. The neutral gas becomes charged again. And the instant that happens, the universe becomes opaque. This is worth slowing down for, because the physics is simple and the consequence is enormous. Light travels freely through neutral gas. It does not travel freely through charged particles. Free electrons scatter photons constantly, in every direction, like fog scattering the beam of a headlight. In fog, the light from your headlight does not travel forward. It bounces immediately off a droplet, and then off another and another, so that you are standing inside a glow with no direction to it, and you cannot see anything more than a few meters away. Before 380,000 years, the entire universe was that fog. Every photon traveled a tiny distance and was knocked sideways. Light existed in enormous quantity, but it went nowhere. There was no seeing, there was no across. There was brightness with no visibility, which is a strange combination and worth holding for a moment. Blinding and blind at the same time. And when we look at the oldest light we can detect, the faint microwave glow that fills the sky in every direction, we are looking at the moment the fog cleared, the surface of last scattering, the place where a photon bounced for the final time and then found nothing in its way and traveled onward for 13.8 billion years and ended in an antenna in New Jersey, and in every detector we have built since, and in the room where you are lying. That surface is the edge of our vision, not the edge of the universe, the edge of what light can show us. Behind it, the fog is still there, and it will always be there, and no telescope of any size will ever see through it. Everything from here on is inference. We do not see it. We reconstruct it from physics we have tested in laboratories, run backward into conditions we cannot photograph. Say that plainly to yourself before we go further. From this point on, you are walking in the dark with a good map. Keep running the film. Now the temperature climbs steeply. Thousands of degrees becomes tens of thousands, becomes millions. The universe is a plasma, a soup of bare nuclei and free electrons and light, all of it interacting constantly, all of it packed close. Density is the thing to feel here, and density is hard to feel. So let me try to put it into your hand. Take a cubic centimeter, a small sugar cube. Hold that volume in your fingers and think of how little it is. In the air of the room around you, that volume contains a certain modest number of molecules, drifting, mostly missing each other. In water, it contains about a gram of matter, which is nothing, a drop. Run the universe backward far enough, and that same sugar cube of space contains as much matter as a cube of water, then as much as a cube of stone, then as much as a cube of lead, then more than the core of the sundae, then more than anything you have ever touched or could touch. And it is not a lump in the middle of somewhere, it is everywhere. Every cubic centimeter in the universe is that dense, at once, with no thin regions and no gaps. Hold that for a moment. Keep running. At about 3 minutes after the beginning, going forward, the universe was cool enough for protons and neutrons to stick together into the nuclei of light elements. Helium mostly, a trace of lithium. Almost everything else came much later, inside stars. Run it backward and you watch those nuclei come apart. Helium dissolves into its separate protons and neutrons. The building blocks refuse to stay stuck because the surrounding energy is too fierce, and anything that binds is immediately broken again. This matters more than it sounds, because it is one of the strongest pieces of evidence we have that this reconstruction is not a fantasy. The theory predicts a very specific ratio of hydrogen to helium coming out of those 3 minutes. Roughly 3/4 hydrogen, 1/4 helium by mass. And when we measure the composition of the oldest and least polluted gas we can find in the universe, that is what we see. Not approximately, precisely, within the error bars, across independent measurements taken in completely different ways. 2 men found the leftover light by accident. Others counted the leftover helium on purpose. The 2 answers agree, and they were arrived at from opposite directions. That agreement is why this is science and not story. Now go further back than 3 minutes, and the ordinary landmarks begin to disappear. 1 second after the beginning, the universe is roughly 10 billion degrees. There is no material anywhere that could exist at that temperature. Every substance you know of, every metal, every ceramic, every element in the periodic table is vapor long before this. Then the vapor is stripped of its electrons. Then the nuclei themselves are shattered. There is nothing here that could be called a thing. At 1 second, protons and neutrons exist, but they are converting back and forth into each other constantly, and neutrinos are streaming everywhere and interacting with everything. Those neutrinos, incidentally, are still here. They decoupled at about this moment and have been traveling ever since. A second background hidden under the light background, far too faint for us to detect directly with current instruments. They pass through the Earth without noticing it. They pass through you. There are roughly 300 of them in every cubic centimeter of the space around you right now, arriving from a moment 1 second after the beginning of the universe. You are, at this instant, being rained on by the first second. Let that land for a second. Keep going backward. 1 second becomes a millisecond. Now the protons and neutrons themselves stop being able to hold together. Each of them is made of smaller things, quarks, bound by a force so strong that under ordinary conditions you cannot pull them apart. Try to separate two quarks, and the energy you put in creates new quarks rather than letting the old ones go free. It is the one force in nature that gets stronger the further you pull. But heated enough, and even that fails. Above a certain temperature, the protons and neutrons dissolve, not into pieces, into a state where the pieces are no longer assigned to any particular parent. A hot fluid of quarks and the particles that bind them, flowing freely with no individual identity, no ownership, no this quark belongs to that proton. We have made this. Briefly, in colliders, on Earth, in the last few decades, we have smashed heavy nuclei into each other hard enough to recreate, for an unimaginably short instant, in a volume smaller than an atom, the state the entire universe was in at a fraction of a millisecond old. It behaved, when we made it, like a liquid with almost no friction. The most perfect fluid that has ever been measured. That is what everything was. Not solid, not gas. A perfect liquid with no parts that belong to anything. Go further back. Now, the distinctions between the forces of nature begin to blur. At the temperatures we are approaching, electromagnetism and the weak nuclear force stop being two things. They merge into a single unified interaction, and the particles that carry the weak force lose the mass they have in the cooler universe you live in. This is not speculation dressed up as fact. It is the physics that the Large Hadron Collider was built to test, and the particle whose discovery confirmed it was found in 2012. So even the laws are changing as you walk backward. Not the deep laws, the way they present themselves. What look to you like separate forces with separate strengths and separate carriers are, at sufficient energy, aspects of one thing wearing different clothes. Keep going. Now we are into territory where the experimental floor gives out. Beyond the energies our machines can reach, the extrapolation continues, but nothing is testing it directly anymore. There may have been a unification of the strong force with the others. There may have been the moment when matter and antimatter, produced in what should have been equal amounts, ended up with a tiny surplus of matter, roughly 1 part in a billion, and that surplus is everything. Every star, every planet, the stone in your hand, the leftover, everything you have ever seen is the rounding error. Sit with that, and somewhere in here, extremely early, according to the picture most cosmologists work with, the universe underwent a brief episode of expansion so violent that it makes everything since look motionless. A period lasting a fraction of a second, in which space grew by an enormous factor, smoothing out irregularities, flattening the geometry, and stretching microscopic quantum fluctuations into the enormous ripples that would eventually become the pattern in that ancient light and, much later, the arrangement of the galaxies. The largest structures in the universe, in that picture, are quantum accidents that got enlarged. Whatever grew from that episode, the fluctuations that seeded every galaxy, was once smaller than an atom. Now keep running the film. there is not much left. Because as you go back further, the pattern is relentless and it does not slow down. Temperature climbs without limit. Density climbs without limit. The volume containing everything shrinks and shrinks, and the shrinking does not become gradual as you approach the start. It accelerates. Everything that was ever going to exist is packed into a volume smaller than an atom, then smaller than a nucleus, then smaller than anything for which we have a word. And here is what general relativity says. If you take the equations that have described every stage of this walk, the equations that predicted the expansion before anyone measured it, the equations that describe the bending of light around the sun and the orbits of the planets and the ticking of the clocks in the satellites over your head, and you simply keep running them backward, they say the density becomes infinite, not very large, not larger than we can measure, infinite. And the curvature of space-time, the quantity that describes how thoroughly geometry is bent, also becomes infinite. And the volume containing everything goes to zero. Not small, zero. Let me say that again so it registers. Take our best and most thoroughly tested theory of gravity, feed it the universe we actually observe, and run it backward, and it terminates in a state of infinite density and infinite curvature and zero size a finite time ago. That is the destination of the reverse walk. That is where the film runs out. And when I say the film runs out, I am choosing my words carefully, because something happens at that point that I am not going to describe to you yet. Not because it is complicated, because it deserves its own space, and because if I say it now, it will arrive as a fact and slide past you, and it should not slide past you. It should be the thing that reorganizes everything else. For now, notice only this. Every stage of the walk we have just done was a real place. The dark ages were real. The fog was real. The perfect liquid was real. And we have made a droplet of it on Earth. Each of those stages was a physical condition, describable, in principle photographable if you had survived, to be there with a camera and something to see by. The end of the film is not like that. The end of the film is not a place. It is a behavior of the mathematics. And when a theory that has been right about everything else starts producing infinity, the honest question is not, what does the infinity look like? The honest question is a different one entirely, and we will ask it next. Something happens to the equations there. I am not going to tell you what yet. Run your thumb across the stone. Feel the surface close. Nothing to hold on to. Not yet. Here is what happens to the equations. They stop producing answers. That is all. There is no flash, no revelation, no moment where the mathematics opens onto something unspeakable. The equations simply cease to say anything you could use. You put in the conditions of the early universe. You run the calculation backward, and at a certain point the quantities you are tracking stop being numbers. Density does not become enormous, it becomes infinite. Curvature does not become extreme, it becomes infinite. Volume does not become tiny, it becomes zero. And infinity, in a physical equation, is not a measurement. I want to spend a long time here because this is the hinge of everything, and it is very easy to walk past it. Almost every popular telling of the beginning of the universe walks past it. They say the universe began as a singularity, a point of infinite density, and then they move on as though a description has been given. But nothing has been described. A word has been used. So let us take it apart slowly. When a physical theory returns an infinite answer, there are two possible readings, and they lead in completely different directions. The first reading is that the infinity is real, that there genuinely was a moment when the density of everything was without limit, when the geometry of space was bent beyond any possible measure, when the entire contents of the universe occupied exactly no volume at all. That the theory is telling you the truth, and the truth is simply monstrous. The second reading is that the infinity is a signal, that the theory has been taken outside the conditions where it works, and is now producing output the way a calculator produces output when you divide by 0. Not a result, an error message. A polite indication that the question, as posed, has left the domain of the tool. Physics has been in this position many times before, and almost every time it has been the second reading that was correct. Let that land for a second. Here is a homely example. Take the equations that describe the flow of water and apply them to a wave breaking on a beach. Under certain idealized conditions, the mathematics predicts that the wave face becomes vertical and then that its slope becomes infinite. But nothing infinite happens on any beach anywhere. What happens is that the wave breaks. The idealization stops applying. The smooth, continuous description of water as a fluid gives way to the messier reality of droplets and spray and turbulence, and the infinity was never a feature of the ocean. It was a feature of a description that had been pushed past its limits. Here is another. In the early 20th century, classical physics predicted that an electron orbiting a nucleus should radiate away its energy and spiral into the nucleus in a fraction of a second. Every atom in the universe should collapse instantly. The equations said so plainly, and every atom in the universe conspicuously did not collapse. That failure was not a discovery about atoms. It was the announcement that classical physics could not describe what happens at that scale, and the resolution came from somewhere else entirely, from quantum mechanics, from a new framework that the old equations had no access to. The prediction of catastrophe was correct as mathematics and wrong as physics, and the wrongness was the useful part. It told everyone exactly where to dig. Now, hold that pattern in your mind and look again at the beginning of the universe. General relativity is the most successful description of gravity that human beings have ever produced. This is not a courtesy. It has been tested for over a century in every regime we can reach, and it has never once been caught out. It predicted that light would bend as it passed the sun, and the bend was measured. It predicted that clocks would run at different rates depending on how deep they sat in a gravitational field, and that difference is now corrected for in the satellites that tell your phone where it is, because without the correction the position would drift by kilometers in a day. It predicted that two massive objects spiraling together would radiate ripples in the fabric of space-time itself, and a century later detectors on Earth measured a ripple from two black holes that merged more than 1 billion years ago, and the shape of the signal matched the prediction so closely that it looked like the theory had been drawn over the data. That theory is not a guess. That theory is the best thing we have, and it fails completely at the origin. Both of those things are true. Hold them together without resolving them, because the resolution is the whole point of this part. General relativity is our most thoroughly verified description of gravity, and general relativity produces nonsense at the beginning of the universe. Both are true. There is no contradiction in that pair, though it feels like there should be. A theory can be right everywhere it has been tested and still have an edge. In fact, every theory we have ever built has had an edge. The only question has ever been, where? So here is the sentence I want to hand you. And I want to hand it to you carefully, because it is the thing that most often gets lost. The singularity is not something that happened. The singularity is something that happens to our equations. Say it to yourself in the quiet. The singularity is a feature of the mathematics. It is not a documented event in the history of the universe. Nobody has observed it. Nothing has ever been measured at it or near it. It is what you get when you take a set of equations that were derived and tested under one set of conditions and extrapolate them into a regime where nobody has any business trusting them. And this is not a fringe view or a hedge or a soft way of avoiding a hard fact. This is roughly what most working cosmologists actually think. The singularity is widely regarded not as the first moment of the universe, but as the moment when our description of the universe gives out. The singularity is a real feature of the equations, and it is probably not a real feature of the universe. Both are true. Now, I want to be fair to the mathematics, because there is a version of this that is too easy, and it goes like this. The equations broke, so ignore them. So the singularity was never a problem, so there is nothing to worry about. That version is comfortable, and it is not honest. Because for a long time, it was reasonable to hope that the singularity was an artifact of the simplifying assumptions people were making, and that hope was killed by careful work. Here is what happened. The early solutions describing an expanding universe assumed perfect smoothness. Matter spread evenly, no lumps, no rotation, no asymmetry. And it was very natural to suspect that the singularity was an artifact of that perfection. Real matter is not perfectly smooth. Real collapse is messy. Maybe, people thought, if you allowed for irregularity, the collapsing material would miss itself. Things falling inward would not all arrive at the same point. They would swirl past each other, bounce, scatter, and the infinite density would never occur. The singularity would turn out to be a bookkeeping consequence of an unrealistic assumption. That hope was reasonable. It lasted decades. In 1965, a mathematician named Roger Penrose, working in London, published a short paper that closed the door on it, and he did it by changing the tools. Everyone before him had approached the problem by trying to solve the equations for particular configurations of matter, which meant that every answer applied only to the configuration you had assumed. Penrose did something different. He used methods from topology and from the global study of geometry to ask a question that did not depend on the details. He asked whether, given certain very general conditions, the formation of a singularity could be avoided at all. The answer was no. What he showed was that once a region of collapsing matter passes a certain threshold, once light itself is being drawn inward so thoroughly that even the outward directed rays are converging, then, under a small set of reasonable assumptions, the collapse cannot be halted or deflected. It does not matter how lumpy the matter is. It does not matter whether it is rotating. The geometry is committed. A singularity forms. He was awarded a share of the Nobel Prize in Physics in 2020 for that work, more than half a century after he did it. The citation described the discovery that black hole formation is a robust prediction of general relativity. Robust is the operative word, not a special case, not a curiosity of idealized models, a generic outcome. And then, in the years that followed, Penrose and a young researcher at Cambridge named Stephen Hawking extended the argument in a direction that changed the question entirely. Hawking's insight was to notice that the collapse of a star and the expansion of the universe are, geometrically, the same problem viewed with time running in opposite directions. If a collapsing region must terminate in a singularity, then an expanding region run backward must originate in one. He and Penrose developed a set of theorems that applied not just to matter falling into a black hole, but to the universe as a whole. The conclusion was that under classical general relativity, given the kind of universe we appear to live in, a singularity in the past is not optional. It is not an artifact of assuming smoothness. It cannot be dodged by making the model more realistic. If general relativity is the correct and complete description of gravity, then the universe had a first moment at which the description itself fails. Now here is the part I want you to appreciate, because it is the part that gets told backward almost everywhere. The singularity theorems are frequently presented as proof that the universe began at a singularity. That is not how they are read by the people who work with them. They are read as a proof of something else. They are read as a proof that classical general relativity cannot be the final theory. Think about the logic. The theorems say that if general relativity holds all the way down, a singularity is unavoidable. A singularity is a place where the theory stops producing meaningful answers. Therefore, if general relativity holds all the way down, general relativity guarantees its own breakdown. Any theory that predicts, from its own internal machinery, that it will fail is telling you something true, but what it is telling you is about itself. Hawking said as much, repeatedly, in later years. He described the singularity result as demonstrating not that the universe began in an infinitely dense point, but that general relativity must break down before you get there, and that whatever replaces it must be a theory that includes quantum mechanics. The theorems were not the end of an inquiry. They were an instruction about where to dig. Both of these things are true. The theorems proved that a singularity is unavoidable in classical general relativity, and the theorems are the strongest evidence we have that classical general relativity does not describe the origin. Hold both. So, why quantum mechanics? Why is that the obvious place to look? Because of a simple fact about scale. The two great frameworks of 20th century physics divided the world between them, and the division has held for 100 years. General relativity describes gravity, and gravity matters when there is a lot of mass and a lot of space. Planets, stars, galaxies, the bending of light across the cosmos. It is the physics of the enormous. Quantum mechanics describes everything else, and it matters when things are very small. Atoms, electrons, the behavior of light when you look closely enough. It is the physics of the tiny. For almost everything in the universe, this division is convenient rather than troubling. Something is either large and heavy or small and light. If it is large and heavy, you use general relativity and you can safely ignore quantum effects. If it is small and light, you use quantum mechanics and you can safely ignore gravity, because gravity between individual particles is so absurdly weak that it does not register. Two electrons attract each other gravitationally, in principle. In practice, the electrical repulsion between them is stronger by a factor with more than 40 zeros in it. But the early universe is both. It is everything that exists, which is a great deal of mass and energy, compressed into a region small enough for quantum effects to dominate. Both regimes are screaming at once. You cannot ignore gravity because the density is beyond anything imaginable. You cannot ignore quantum mechanics because the volume is smaller than a subatomic particle, and when you try to use both at the same time, the mathematics does not cooperate. This is not for lack of effort. Some of the most capable people in the history of physics have spent entire careers on it. The problem is deep and structural. General relativity treats space-time as a smooth, continuous geometry that is bent by matter. Quantum mechanics treats things as fundamentally uncertain and fluctuating, never quite having a definite value until measured. Ask what happens when the geometry itself is uncertain, when space and time are fluctuating, and the standard techniques come apart in your hands. The calculations produce infinities that cannot be tidied away by the methods that work everywhere else in quantum physics. There are candidates. There are serious research programs that have absorbed decades of work from very good people. String theory, loop quantum gravity, various approaches to a quantum description of space-time that I am not going to catalogue tonight. Some of them are mathematically beautiful. Some of them make suggestive statements about the early universe. None of them has been confirmed by observation. Not one. Not a single prediction from any theory of quantum gravity has been experimentally verified. That is the honest position, and I am not going to dress it up. So we have a wall, and the wall has a name and a location, and I want to give you a felt sense of where it stands. The name is the Planck epoch, and it refers to a regime defined by combining the constants that govern gravity, quantum mechanics, and the speed of light into a single length and a single duration. It is the scale at which both frameworks must apply simultaneously, and therefore the scale at which having only one of them is useless. The length is roughly 100 million trillion times smaller than a proton. That comparison does no work at all. So let us build it up in steps you can stand on. Start with your hand, hold it out in front of you and look at it. The width of your palm, call it 10 centimeters. Now imagine shrinking down by a factor of 1,000,000. You are now the size of a bacterium sitting on your own skin, and your palm has become a landscape the size of a large city. Shrink by 1,000,000 again. Now you are far smaller than an atom. The bacterium you were standing on has become a world larger than the Earth. Shrink by 1,000,000 a third time. You are now down among the components of an atomic nucleus, in territory that only exists in the output of particle detectors. Do it again, and again, and again. You have to perform that shrinking by a factor of 1,000,000, 6 times over, and then a little more before you arrive at the Planck length. There is no instrument and no plausible design for an instrument that could probe that scale. To see something small, you need a probe with a short wavelength, and short wavelengths mean high energies, and the energy required to resolve the Planck length would need a particle accelerator of a size we would not know how to begin building. Some estimates put it at the scale of a galaxy, and the duration is worse. The Planck time is how long light takes to cross the Planck length, and light is fast. It is the shortest interval that has any operational meaning in current physics. Compared to 1 second, the Planck time is smaller than 1 second is compared to the entire age of the universe. By an enormous margin, you could line up the whole history of the cosmos, 13.8 billion years, every star, every planet, every extinction, every generation of every species that has ever lived. And that entire span would be a longer interval relative to 1 second than 1 second is relative to the Planck time, many times over. Hold that for a moment. That is the wall. Everything before that, in the reverse walk we did together, is territory where our physics simply has nothing reliable to say. Not that the answers are difficult, not that the calculations are unfinished, that we do not possess the theory required to make the calculation meaningful in the first place. And now I want to be very careful and very quiet about what that means, because I promised you honesty rather than comfort, and we are at the point where the two come apart. We do not know what happened at the beginning. That is not a rhetorical setup. It is the state of the field in 2026. We have an extraordinarily detailed and well-tested account of the universe from a tiny fraction of a second onward. We can tell you the temperature at 1 second. We can tell you the ratio of helium to hydrogen that came out of the first 3 minutes and check it against observation. We can map the light released at 380,000 years to a precision that would have seemed like fantasy 50 years ago. And then there is a wall, and behind the wall there is nothing but proposals. Notice what kind of isolation this is. It is not the isolation of a person alone in a room. It is not personal at all. It is geometric, and it is epistemic. There is a boundary on what can currently be known, and it is not a boundary we drew, and it is not a boundary we can argue our way past. It is where our instruments end and our theories end at the same place. Everyone who has ever lived has stood on this side of that wall. Every physicist you could name, every telescope ever built, every observation ever recorded, every measurement in every laboratory on Earth, all of it is on this side. Nobody has ever been on the other side. There is no accumulated body of knowledge slowly working its way inward. There is a hard limit and 100 years of very intelligent people pressing against it. That is the situation. Sit in it for a moment before we go on. The mathematics stops speaking, not into darkness, into silence. And silence is not an answer. Not yet. Let us leave the physics alone for a while and take a walk. Imagine you are standing somewhere in the middle latitudes, on ordinary ground, with a compass in your hand. The needle settles. It points north. You start walking in that direction, and you keep going. You cross farmland and then forest. The trees thin out and become smaller and more stubborn. You cross a line somewhere where the trees stop entirely, and after that there is tundra, low scrub, ground that stays frozen a meter down all summer. You keep going north. The land gives out and becomes coast, and the coast gives out and becomes sea ice, and you keep walking north across the ice, and the sun stops setting properly, and the compass needle keeps pointing the way it has pointed the whole time. North. Still north. Always available, always further. Now notice something. At every single moment of this walk, no matter where you were, north existed. It was a real direction. You could point at it. There was more of it ahead of you. Every step you took, you could have taken another one in the same direction, and you would have been further north than you were before. Keep going, and then, at a certain point on the ice, you take one more step, and something quiet happens. You are standing at the North Pole. Take a moment there. It does not look like anything. There is no marker, there is no pillar, no line, no wall, no edge. It is a patch of drifting sea ice that looks exactly like the ice you crossed an hour ago. If you had not been counting your position, you would not know you had arrived. But now, try to keep walking north. You cannot. And notice, carefully, why you cannot. It is not that there is a barrier. Nothing is stopping you. The ice continues perfectly happily in every direction. You can walk as far as you like. You have plenty of ground under your feet, and the world does not end. But whatever direction you step, you are now going south. Every direction. There is no exception. There is no clever route. From that patch of ice, every conceivable path leads south, and this is not a rule that was imposed on you, and it is not a limit on how far you may travel. It is simply what north means, exhausted. Now stand there and ask the question, what is north of the North Pole? Look at the sentence. It is a perfectly formed English sentence. Every word in it is a real word with a real meaning. North is a genuine direction. The North Pole is a genuine place with genuine coordinates. Of is doing ordinary work. You can say it aloud, and anyone who speaks the language will understand every component of what you said, and nobody will interrupt you to say that you have made a grammatical error, because you have not made one, and there is no answer. There is not a hidden answer, or a difficult answer, or an answer that requires better equipment to obtain. There is nothing there for an answer to be about. Let that land for a second. This is a very particular kind of failure, and I want you to feel its texture, because it is unlike the other kinds. It is not like asking how many stars are in the galaxy, where the answer exists and is merely hard to count. It is not like asking what is at the bottom of the ocean in a place nobody has visited, where the answer is waiting and we simply have not gone. It is not even like asking what happened before recorded history, where the answer existed and the records were lost. It is a question that has emptied out. The words remained, and the geometry underneath them quietly withdrew. And crucially, nothing about the words themselves warns you. You cannot tell by inspecting the sentence. It looks exactly like a question that would have an answer. It sounds like one. It feels, when you ask it, like the sort of thing somebody ought to be able to tell you. The emptiness is not in the language. It is in the world the language was pointing at. And the sphere is not defective. That is the other thing worth noticing. There is nothing wrong with the Earth. The Earth is not missing a piece. The surface of the planet is complete, continuous, unbroken, with no hole where the answer should have been. You can walk across every part of it. The absence of anything north of the pole is not a gap. It is a property of a closed surface, and closed surfaces are perfectly ordinary things. Which brings me back to the object in your hand. Pick up the stone again. Run your thumb across it the way you did at the very beginning, slowly, in a long arc, around the curve and over the top and down the far side. Finite surface. You could measure it in a moment. Bounded, in the sense that there is only so much of it, and no edge, no rim, no first point. Nowhere on that surface where the surface begins. You noticed this at the start of the night, and I asked you to hold it without explanation. Here is the explanation. A thing can be finite and have no boundary. Those two properties do not conflict. They only seem to conflict because almost everything you handle in ordinary life has both a limited extent and an edge. So the two ideas have fused in your intuition into a single expectation. A table is finite and has a rim. A page is finite and has a margin. A room is finite and has walls. So finite comes to mean edged, and the fusion happens below the level of thought. But the surface of the stone is finite and edgeless. So is the surface of the earth. So is the surface of a ball or an orange or a soap bubble. These are not exotic objects. You have been surrounded by them your whole life. Every one of them is a finite thing without a boundary, and none of them has ever struck you as paradoxical, because you have never tried to look for their edge. Now, put the two together, the pole and the stone, and turn them toward time. Here is the proposal. In 1983, two physicists published a paper together. One was James Hartle at the University of California at Santa Barbara. The other was Stephen Hawking at Cambridge. The idea had grown out of a summer visit and a series of conversations, and when it was written down, it was short and it was strange, and it has been argued about ever since. They asked what the initial condition of the universe should be. This is a technical question with a very ordinary shape. Physics generally works by taking a state of a system and evolving it forward according to some rule. To describe the universe, you need both the rule and the starting state. The rule is the physics. The starting state has to be specified separately, put in by hand, chosen. And this had always been unsatisfying, because it meant the universe required something from outside the theory, some initial arrangement that the theory could not account for and simply had to be handed. Hartle and Hawking proposed something different. They proposed that the boundary condition of the universe is that it has no boundary. Now hold on to that phrasing, because it sounds like wordplay and it is not. It is a specific technical suggestion about the geometry of space-time near the origin, and I am going to try to give you the shape of it without any mathematics at all. Think about how you normally picture time. A line, an arrow, a stretched thread running from left to right, with the present as a bead sliding along it. If the universe began, then somewhere on the far left there is an end of the thread, a first point, a place where the line starts and before which there is nothing. And that first point is a boundary. It is an edge, which means it needs to be explained or specified or accounted for by something. The no boundary proposal suggests that time, very near the origin, does not behave like a line at all. It suggests that in that regime, where quantum effects on gravity cannot be ignored, the distinction between the time direction and the space direction softens. Time stops being a separate thing that runs perpendicular to space and starts behaving, in the mathematics, more like another spatial dimension. And if that is what happens, then the geometry near the origin is not a line with an end. It is a surface that curves smoothly closed. Picture the pole again. Picture the surface of the stone. The thing that happens at the North Pole is not that the surface stops. It is that a particular direction, north, ceases to be available while the surface itself continues perfectly smoothly in every other sense. Nothing is torn. Nothing has an edge. The direction simply runs out because of how the geometry closes. In the no-boundary picture, the beginning of the universe is like that. Not a first instant with nothing before it, sitting there requiring explanation. A place where the time direction runs out because the geometry closes smoothly, the way north runs out at the pole. There is no earlier moment to stand in, and there is no edge to stand before, and there is no missing piece where the edge should have been. Hawking used the North Pole comparison himself more than once in lectures given over the last decades of his life. He described asking what came before the Big Bang as being like asking what lies south of the South Pole. The words assemble correctly. The geometry has nothing to hand them. Now, I want to be extremely clear about the status of this idea, because I've just spent several minutes making it sound persuasive, and it is important that you know exactly what you are holding. This is a proposal. It is not an established result. It is not a measurement. It is not something the community has agreed upon. It is a serious, technically detailed suggestion made by two very capable physicists, and it has been the subject of vigorous and continuing disagreement for more than 40 years. The disagreement is not polite background noise. In recent years, physicists, including Neil Turok, working with colleagues, published analyses arguing that when the calculation is done with more modern mathematical techniques, the no-boundary proposal does not give the universe we observe at all, but predicts wild and unacceptable fluctuations. Other physicists, including Thomas Hertog, who worked closely with Hawking for the last 2 decades of his life, disputed both the technique and the framing, and the argument traced itself back to genuinely deep disagreements about how to do quantum mechanics for an entire universe when there is nobody outside it to do the measuring. That argument has not been settled. It cannot currently be settled by observation because we have no way to observe the regime in question. So do not walk away from tonight thinking that the question has been answered and this is the answer. It has not been. This is one carefully constructed possibility, and it is contested, and the people contesting it are not cranks. But here is why it matters even so, and why it is worth an hour of your attention on a night when you are trying to fall asleep. It demonstrates that the question can fail to have an answer without anything being missing. That is the load-bearing insight, and it does not depend on the proposal being correct. Even if the no-boundary picture turns out to be wrong in every technical detail, it has already shown something true, which is that a universe with a finite past and no first moment is a coherent thing to describe. It is not a contradiction. It is not a dodge. Somebody wrote down what it would look like in mathematics, and other people have been checking the mathematics for 40 years, and the disagreement is about whether it matches our universe, not about whether the concept makes sense. Before that paper, one could reasonably think that a universe with a beginning must have a first instant, and that a first instant must have something before it, or must be an arbitrary edge requiring explanation. After it, that is no longer obviously true. the space of possibilities got wider. Let that land for a second. Now let us go the rest of the way, because there is a philosophical version of this that does not depend on any particular proposal at all, and it is older and simpler, and it has been sitting there the whole time. If time itself began with the universe, then the word before has nothing to refer to. Look at what before actually means. It is a relation. It describes the position of one moment relative to another moment on a shared timeline. To say that event A came before event B is to say something about how they sit in relation to each other in time. The word only functions when there is a temporal framework for it to operate in. Remove the framework and the word does not become false, it becomes inapplicable, the way north becomes inapplicable at the pole. So when you ask what came before the beginning of time, you are asking for a moment that is earlier than the earliest moment, not a hidden one, not one we lack the instruments to see, one that the structure of the question has already ruled out, in the same way the structure of the sphere rules out anything north of the pole. And the same thing happens, more painfully, to cause. Causation is something we are extraordinarily attached to, and for excellent reasons. You have never in your life encountered anything that happened without something making it happen. The chain runs backward from every event, unbroken, as far as you care to trace it. It is the deepest habit your mind has. But notice what causation requires. A cause precedes its effect. The cause is earlier. The effect is later. Causation is not merely something that happens in time. It is defined by a temporal ordering. Take away the ordering, and you have not got a mysterious, causeless event. You have a concept with nothing to grip. So the question, what caused the universe, asked about the origin of time itself, is not a hard question that physics has failed to answer. It is a question that imports the very thing it is asking about. It assumes a before in order to ask about the beginning of before. It assumes a temporal ordering in order to ask about the origin of temporal ordering. This is the same failure as north of the pole, wearing more serious clothes. And this is not a modern insight, incidentally, though the physics is modern. Something close to it was written down in the 5th century by Augustine, who argued that God did not create the world in time, but created time along with the world, and that asking what God was doing before the creation was a confused question because there was no before to be doing it in. He was working from theology and not from general relativity, and he had no equations, and he reached a structurally identical conclusion 1600 years early. The idea has been available for a long time. What has changed is that it is now something the mathematics can express. Now, sit still for a moment and notice how you feel, because I think something shifts here and it is worth catching. We spent the last part in a fairly bleak place. There was a wall and we could not see past it, and I told you plainly that nobody has ever been on the other side. That was true, and I am not taking it back. But look at what has just happened to the question. We were treating what came before the Big Bang as an unanswered question, something with an answer, locked away behind the wall, tantalizingly out of reach, which we might never get. And an unanswered question of that kind sits badly. It feels like a debt. It feels like something owed to you that you are not going to be paid. But if before is inapplicable, then there is no debt. Nothing is being withheld. There is no locked room with the answer in it. There is no fact of the matter. that we are failing to reach. The vault is not sealed. There is no vault. This does not make the wall disappear. The Planck epoch is still there, and our physics still gives out. But the thing we were most upset about losing may not have been a thing at all, and that is a different feeling entirely from being shut out. Consider the difference between two situations. In the first, someone knows something about you and will not tell you. In the second, there is simply nothing to know. The first is unbearable and the second is not. And the difference is not in how much information you have. It is identical in both cases. The difference is entirely in whether something is being kept from you. Nothing is being kept from you tonight. There may not be a before. There may be nothing there of the kind you were reaching for. And if that is so, then the ache you feel when you ask the question is not the ache of exclusion. It is the ache of a mind trying to perform an operation on a structure that does not support it, like trying to walk north from the pole, like trying to find the edge of a stone. Both of these things are true, and I want you to hold them together as we go on. We do not know what happened at the origin, and the thing we most want to know may not be a thing. That is not a contradiction. That is the honest shape of where we are. Now, the stone is still in your hand, finite, edgeless, complete, nothing missing, nowhere it begins. I have just spent a long stretch of tonight walking you carefully toward one idea, and now I have to do something that might feel like taking it away. The no boundary picture is one door. It is not the only door. There are others, built by other people, opening in other directions, and some of the people who built them think the door I just showed you does not open at all. This is not a weakness in the field. It is what an honest field looks like at its frontier. When a question is genuinely open, serious people disagree, and they disagree in public, in print, for decades. If I showed you one framing and closed the video there, I would be handing you a settled picture of an unsettled place, and that would be a small lie told for the sake of a tidy ending. So let us go through 3 of the others, slowly, one at a time, each of them held up to the light and turned around, and each of them put back down without a verdict, because I do not have a verdict to give you, and neither does anyone else. I want to say one thing before we start, and I want to say it plainly so that it sits underneath everything that follows. Every idea in this part lives beyond the wall, all of it. Every proposal, every model, every carefully worked out alternative, all of them describe the regime we cannot see into. None of them has been confirmed by observation, and several of them may never be, and the people who work on them know this better than anyone. What follows is not a list of discoveries. It is a survey of possibilities that intelligent people have found worth taking seriously. Hold that as we go. Start with the first door, which comes out of the physics we already touched on tonight. You will remember that somewhere in the reverse walk, extremely early, I mentioned a brief episode of enormously rapid expansion. A fraction of a second in which space grew by a colossal factor, smoothing the geometry, flattening the curvature, and stretching microscopic quantum fluctuations into the pattern that would eventually become the arrangement of galaxies. That episode is called Inflation, and it was proposed in 1981 by Alan Guth, then a young physicist working at Stanford and later at the Massachusetts Institute of Technology. Inflation was introduced to solve specific problems. The universe looks remarkably uniform across regions that should never have been in contact with each other. Its geometry is remarkably flat when the equations suggest it should have curved away from flatness over time. A brief burst of exponential expansion handles both at once, and it does so elegantly. And it also produces, as an unplanned bonus, exactly the kind of density variations we observe in the ancient light. That is a strong record for one idea, and it is why inflation became the standard framework rather than a curiosity. But then people started asking how inflation ends, and the answer turned out to be stranger than the original proposal. Inflation is driven by a field filling space, holding a particular kind of energy that makes space push itself apart. Inflation stops in a given region when that field rolls down out of its high energy state and releases its energy as hot matter and radiation. That release is what we usually call the Big Bang. The heat of the early universe in this picture is not the beginning of everything. It is the end of inflation in our patch. Here is the difficulty. The field is a quantum field, and quantum fields fluctuate. So the roll down does not happen everywhere at once. It happens here, then there, patchily, at random. And meanwhile, the regions where it has not yet happened are still inflating, still doubling again. Work through the arithmetic and you find something disorienting. The regions that stop inflating become ordinary universes like ours, expanding at a leisurely rate. The regions that keep inflating grow exponentially. So even though inflation constantly ends in more and more places, the total volume still inflating grows faster than the total volume that has settled down. The process, once started, never finishes globally. It only finishes locally. Guth and, independently, André Linde, working first in Moscow and later at Stanford, developed this into what is now called eternal inflation. Linde, in particular, pushed the picture hard through the 1980s in a series of papers describing a universe that is eternally self-reproducing, endlessly generating new regions where inflation halts and a hot expanding cosmos begins. Sit with the shape of that for a moment. In this picture, what you call the universe, the entire observable cosmos, everything within 13.8 billion years of light travel, every galaxy in every survey, is one bubble, one region where the field happened to roll down at one moment, and beyond it, unreachably far outside our horizon, the inflating background continues, and other bubbles form in it, constantly, and each one of them is a universe with its own hot beginning and its own history, and possibly its own physical constants. The bubbles are separated by space that is still inflating, which means the gap between any two of them is growing faster than light can cross it. They can never meet, they can never signal. Each one is complete and isolated and does not know the others exist. Now notice what this does to our question. In this picture, there was a before. There was something prior to our hot, dense beginning, and it was not nothing. It was an inflating region of space, existing already, doing what it does, and our universe is what happened when a patch of it stopped. The question, what came before the Big Bang, gets an answer. It just does not get the answer you were reaching for, because the before belongs to the inflating background rather than to us, and the inflating background is not our universe. and never was. And then you can ask the same question about the background, and the honest position is that it does not obviously help. Guth himself has been careful about this in print. In a review paper on eternal inflation and its implications, he noted that although inflation is generically eternal into the future, it is not eternal into the past. Under reasonable assumptions, it can be shown that an inflating region must be incomplete in the past direction, which means that some physics other than inflation is needed to describe how the whole structure began. Read that carefully. The person most associated with the idea is telling you that the idea does not solve the problem. It moves the problem outward. There is still a boundary somewhere back there, and inflation does not describe it. So what would count as evidence? This is where eternal inflation becomes difficult in a way that troubles even its supporters. The other bubbles are permanently beyond our horizon, which means we cannot observe them, which means the multiplicity of universes is not directly testable. There have been searches for one very specific signature, which is a possible collision between our bubble and a neighboring one early in our history, which some models suggest could leave a circular imprint on the ancient light. People have looked. Nothing conclusive has been found. There is also a deeper problem that Guth discusses at length, which is that in an eternally inflating cosmos, anything that can happen happens infinitely many times, and comparing infinite quantities to extract probabilities turns out to depend on arbitrary choices about how you count. Different reasonable counting schemes give different answers to the same question. That is not a small technical annoyance. It undercuts the ability of the framework to predict anything at all. So eternal inflation is a serious idea, following from a well-supported theory, with genuine explanatory reach and a genuine and unresolved difficulty at its foundation. Hold that for a moment, and then let us open the second door. The second door starts from a different instinct entirely, and the instinct is this: rather than accepting the singularity and building around it, why not get rid of it? These are the bounce cosmologies, and the family is large and varied and has been developed by a number of groups over several decades, including Paul Steinhardt at Princeton, Neil Turok, and Anna Ijas, among many others. The core idea is simple to state. Suppose that instead of a beginning, there was a contraction, a previous universe or a previous phase of this one, shrinking rather than growing. The density rises as it contracts. The temperature rises. Everything approaches the extreme conditions we described in the reverse walk. And then, instead of reaching infinite density, it reaches a minimum size and turns around. The contraction becomes an expansion. What we call the Big Bang was not a first moment. It was a turning point, a bounce, and on the far side of it there is a genuine before, filled with a genuine prior history, running in the opposite direction. This is attractive for reasons beyond the removal of the singularity. Some versions of it also solve the uniformity and flatness problems that inflation was invented to handle by a completely different mechanism. Instead of stretching an irregular patch until the irregularities become invisible, a slow contraction squeezes irregularities out of significance as everything is compressed. Steinhardt has argued that this produces a smoother and flatter outcome more reliably than inflation does, and without generating the endless multiplicity of bubbles. Simulations published in recent years have shown that a contracting phase can indeed produce the required smoothness and flatness before the bounce occurs, which was one of the main technical objections and which those results substantially addressed. Now here is the difficulty, and it is a large one, and everyone in the field states it openly. We do not know how to make the bounce happen. To turn a contraction into an expansion, you need something that resists the collapse and reverses it at the last moment. In ordinary general relativity with ordinary matter, that does not happen. Gravity pulls inward and the collapse continues, which is precisely what the singularity theorems established. To get a bounce, you need either exotic matter with unusual properties, or a modification to gravity itself, or quantum effects that become dominant at the turning point and push back. Every one of those is speculative. Some approaches use quantum gravity frameworks such as loop quantum cosmology, in which the discreteness of space at very small scales creates an effective repulsion that halts the collapse. Others use scalar fields with carefully chosen properties. Others modify the gravitational equations. None of these mechanisms has been observed, not one. The bounce, which is the entire point of the picture, is the part we cannot describe with confirmed physics. So a bounce cosmology replaces one thing we cannot describe, the singularity, with another thing we cannot describe, the turning point. That is not nothing. A turning point is at least the kind of thing that could in principle be a physical event, whereas a singularity is not. But the honest summary is that the difficulty has been relocated rather than eliminated. What would count as evidence? This is more promising than for eternal inflation, because a contracting phase and an inflating phase leave different fingerprints. The pattern of ripples imprinted in the ancient light depends on whether space was expanding or contracting when those ripples were generated. Work by several groups has shown that the way density variations behave across different scales should differ between the two scenarios, in ways that future surveys might be able to distinguish. There is also a cleaner potential discriminator. Inflation predicts that the violent expansion should have generated gravitational waves, ripples in space-time itself, which would leave a specific twisting pattern in the polarization of the ancient light. Bounce models generally predict this signal should be absent or far weaker. Experiments have been searching for that twist for years with increasing sensitivity and have not yet found it. That absence constrains some inflationary models. It does not yet confirm anything. So the evidence is not in. It is possible that it will come in within our lifetimes from instruments already being built. That is genuinely exciting, and it is also genuinely not a resolution tonight. Now the third door, which is the strangest of them, and which I want to describe with care because it is easy to make it sound like poetry when it is meant as physics. This one belongs to Roger Penrose, whom you met earlier tonight, proving that singularities are unavoidable. He has spent much of the last 2 decades developing an alternative account of the beginning, which he calls conformal cyclic cosmology. Follow me carefully, because the logic is unusual. Look forward instead of backward. Ask what happens to the universe in the very far future, and the standard picture is bleak. The expansion accelerates. Galaxies recede beyond each other's horizons. Stars burn out, one by one, over hundreds of trillions of years. The remnants cool. Matter itself may eventually decay. Black holes, which will be the last large structures remaining, slowly evaporate over spans of time so long that the numbers stop conveying anything, and eventually even they are gone. What is left in the extreme far future, is an enormously dilute cosmos containing almost nothing but radiation. Photons, essentially, spread thinly across an unimaginable volume, cold and dispersed and traveling forever. And here is Penrose's observation. Photons are massless. Massless particles do not experience time in the way massive things do. And more importantly, a universe containing only massless particles has no way of measuring scale. To define a size, you need something with a fixed length, and the only fixed lengths available in physics come from particles with mass. Take away every massive particle and you have removed every ruler and every clock from the universe. So in that far future state, the concepts of large and small become meaningless. There is no way, from inside such a universe, to tell whether it is enormous or minute. The distinction has nothing to attach to, and the very early universe, hot and dense and dominated by radiation before matter had settled into its familiar forms, is also a state where mass is largely irrelevant and where scale is similarly slippery. Penrose's proposal is that these two states, the cold, empty, far future of one universe and the hot, dense beginning of the next, are mathematically the same, differing only by a rescaling that has no physical meaning because there is nothing there to measure it against. The far future of one cosmos becomes the beginning of another, not through a collapse, not through a bounce, through the loss of scale. He calls each cycle an aeon. In his picture, the universe is an endless sequence of them, each one running from a hot beginning through stars and galaxies and long cooling to an infinitely dilute end, which is simultaneously the beginning of the next. He has continued to develop the technical machinery for this, including recent work with Christoph Meissner, exploring how the transition between aeons might take place during a period dominated by gravitational waves. So what came before the Big Bang in this picture? The answer is a previous aeon, a whole universe with its own stars and its own long history, whose final cold state is our hot beginning. What would count as evidence? Penrose has argued that events in a previous eon, particularly the collisions of enormous black holes, would radiate gravitational energy that could survive the crossover and appear in our sky as faint circular patterns in the ancient light. He and collaborators have published claims of finding such patterns. Other researchers, analyzing the same data with different statistical methods, have not found them and have argued that the apparent signals are consistent with random fluctuation. The claims are disputed. They have been disputed for over a decade, and I should be straightforward with you about the standing of this idea. Conformal cyclic cosmology is a minority position. Most cosmologists do not work within it. It requires assumptions that many find difficult, including that every particle with mass must eventually decay or lose relevance, which is not established. Penrose is one of the most distinguished living physicists, and this remains, in the view of the field, a speculative proposal without decisive support. I tell you that not to dismiss it, but because you deserve to know where each of these things sits. Now, step back and look at the three doors together. Eternal inflation says the before was an inflating background, and our universe is one bubble among endlessly many. Bounce cosmology says the before was a contracting phase, and the beginning was a turning point, rather than a start. Conformal cyclic cosmology says the before was a complete prior universe whose cold end is our hot beginning, and the no-boundary proposal, which we spent the previous part on, says there may have been no before at all, because time closes smoothly and the direction runs out. 4 pictures, 4 sets of serious people, 4 bodies of technical work developed over decades. They cannot all be right. They may all be wrong. And here is the thing I have to return you to now, because everything in this part has been floating and it needs to be set back down. Every one of these lives beyond the wall, not partly, entirely. The inflating background, the turning point, the previous aeon, the smoothly closing geometry. All of it is in the regime where our physics does not function. On the far side of the Planck epoch, in the territory where general relativity and quantum mechanics both apply, and where we do not possess the theory that combines them, we cannot see past that wall. Not with any instrument that exists, not with any instrument that has been plausibly designed. The proposals differ in what they say lies behind it, and none of them can currently be checked against the thing they describe. That is the honest position, and I am not going to soften it. But notice, before we move on, what has just happened to the feeling in the room. We are not more certain than we were an hour ago. If anything, we are less. When we started this part, you had 1 picture, and now you have 4, and they contradict each other, and yet it does not feel like loss. It feels like the ceiling went up. That is worth noticing, because it is the opposite of what more uncertainty is supposed to do. Standing in front of one closed door is claustrophobic. Standing in a hall with 4 doors, none of them open, is something else. The question did not shrink under examination. It got larger and more interesting and more populated. There are more ways for the universe to be than you thought there were when you lay down tonight. We do not know which door is real. We know the hall exists, and the hall is bigger than we thought. Come back to the stone. It has been in your hand the whole time, through the balloon and the dough, through the fog and the perfect liquid, through the wall and the pole and the hall of 4 doors. You may have forgotten it was there. That is fine. It waited. Close your fingers around it now and feel the weight settle. It is warmer than it was. Your own heat has moved into it over the course of the night, slowly, without either of you doing anything about it. Now run your thumb across the surface, the way you did at the very beginning, slowly, in a long, unhurried arc, around the curve, over the top, down the far side, and back again. Nothing has changed about the stone. Everything has changed about what you are feeling. At the start of the night, you noticed that there was nowhere on that surface that counted as the beginning, and I asked you to hold that without explanation, and you did. Now you know what it was for. A finite thing with no edge. A surface you can travel forever without arriving at a rim. Complete, bounded, and without a first point anywhere on it. The stone is not hiding its edge from you. The stone does not have one. And that is the shape of the thing we have been circling all night. Not an answer withheld. A question that may have nothing to land on. Let me put the honest position down one final time, gently, so it is the last version you carry with you. We do not know what happened at the beginning of the universe. We know a great deal about what happened afterward. We can trace the expansion back across 13.8 billion years with real confidence. We can tell you the temperature at 1 second. We can tell you the proportion of helium that came out of the first 3 minutes, and then go and measure that proportion in ancient gas and watch the two numbers agree. We can map the oldest light in the sky across the whole celestial sphere and read the composition of the cosmos out of the pattern in it. And then there is a wall, and we cannot see past it, and everything on the far side is proposal. That is where the field stands. Not where it will always stand, perhaps, but where it stands tonight, while you are lying there with a stone in your hand. And alongside that, held at the same time, the other thing, the question we most want answered, may not be a question. Before is a relation between moments. Cause is an ordering in time. Ask what came before time, ask what caused causation, and you have not posed a hard problem. You have assembled a grammatical sentence around an empty space, the way you can assemble one about what lies north of the North Pole. Both of those are true, and I want you to hold them together without forcing them to resolve. We cannot see past the wall, and what we are straining to see may not be there to see. Now, I want to say something about how that should feel, because there is a version of tonight that ends in defeat, and I do not think that version is correct. Not knowing is the ordinary condition of understanding. It is not the failure state, it is the working state, and it always has been. Think about what we walked through tonight, and who did the walking. A priest in Belgium following equations into a conclusion his colleagues found uncomfortable, publishing it in a journal almost nobody read, and being quietly ignored for years. A woman at Harvard, cataloguing thousands of variable stars by hand, working as a human computer, producing the measuring stick that made cosmic distance possible at all. A man on a cold mountain in California, 1 photographic plate per night, guiding a telescope by hand, accumulating a graph over years that nobody could argue with by the end. 2 engineers in New Jersey with a hiss in their antenna, cleaning out pigeons, checking the wiring, refusing to let an unexplained noise go unexplained. A mathematician in London who changed the tools rather than the assumptions, and proved something so general it took 55 years for the prize to arrive. A physicist at Cambridge who noticed that a collapsing star and an expanding universe are the same problem with time pointing the other way, and who spent the rest of his life on what that implied. And all the people still working now on the bounce and the bubbles and the aeons, building mathematics for a regime they will probably never see confirmed in their own lifetimes. None of those people knew the answer. Every one of them worked anyway. That is what the enterprise actually is. Not a march towards certainty, a long, patient narrowing of what can be said. Each generation removes a few possibilities, adds a few measurements, tightens the error bars, and hands the whole thing forward to people they will never meet. Lemaitre did not live to see the ancient light mapped from space. Hubble did not live to see the expansion measured to a fraction of a percent. Hawking did not live to see whether his proposal survives the argument it started. They did the work anyway, and the work was not wasted, and the fact that they died without the answer is not a tragedy. It is the arrangement. It is how this has always been done. You are the current holder of the not knowing. That is not a burden. It is a position in a line. And here is the other thing. And this is the part I have been saving. There is something you do every night that has exactly the same structure as the thing we have been talking about, and you have never once found it distressing. You fall asleep. Think about it carefully. When does it happen? Not roughly. Precisely. Name the instant. Name the moment where waking ends and sleep begins. The boundary, the first second of being asleep, the thing that comes just before it. You cannot. And notice that it is not because your memory is poor. It is not because nobody was paying attention. It is because there is no such instant. Sleep does not have a first moment. It is not a line you cross. Consciousness thins and drifts and doubles back and thins further, and the thoughts get less connected to each other. And somewhere in there, the ordinary business of being awake simply stops applying, the way north stops applying. There is no edge, and you have never lost a moment of rest over it. You have never lain there thinking, but what was the last instant? What came immediately before sleep? Why can nobody tell me? The question does not even form. You cross a boundary that has no boundary every single night of your life, and you have never once needed it to be otherwise. You already know how to do this. You have always known how to do this. The universe may simply be doing on the larger scale the thing you do in a bed on an ordinary Tuesday. Let that be enough. Now, the stone, one last time. Feel it in your palm. Warm now, entirely warm, the same temperature as your hand. Run your thumb across the surface, slowly, around the curve, over the top, down the far side. No edge, no rim, no first point, just surface, closing quietly on itself, complete. There is nothing missing from the stone. There is nothing missing from the sky. There is nothing missing from you. The light from the beginning is still arriving. It has been arriving the whole time. It is passing through the room right now, faint and cold, and 13 billion years old, and it does not require you to understand it. The expansion is still happening. It is happening in the space between your hand and the ceiling. It has been happening here. It has been happening everywhere. It has been happening the entire time you have been lying there. You do not need to know how it began. Nobody does. Nobody ever has. Set the stone down now, or keep it, whichever is easier. Let your hand open. Let the weight go. The question can stay where it is. It is not going anywhere. It has waited 100 years for the people who study it, and it will wait a little longer. You are inside the thing you are asking about. You always were. There is no outside to fall from. There is no edge to fall off. Just surface. Just the long, soft curve of it, closing. Sleep well.